Hello and good afternoon and welcome to this summer's fifth and final lecture. There's plenty of seats available, so as you come in, please grab a seat and don't crowd the aisles. Today we're very pleased to hear from Michael Barnett. He's a senior physicist and educator with the lab's physics division, and he'll discuss the Atlas experiment at the Large Hadron Collider. This collider will explore the aftermath of collisions at the highest energies ever produced in the lab, and we'll recreate the conditions of the universe about a billionth of a second after the Big Bang. So it's pretty big stuff. Barnett received a PhD from the University of Chicago and has worked at Berkeley Lab for more than 20 years. He is head of the Particle Data Group, which is an international collaboration with 166 members from 100 universities and laboratories in about 19 countries. And this group provides essential up-to-date summaries of experimental and theoretical physics to the particle physics community. Barnett is also a leader in physics public education. He's the education coordinator of the Atlas experiment, and he led the creation of the Particle Adventure, which is a web multimedia feature now translated in 12 languages that is found at particleadventure.org. Today, he will discuss the Atlas detector. Its goals are to examine, among several things, such as mini black holes, identify dark matter, understand antimatter, search for extra dimensions of space, and learn about the fundamental forces that have shaped the universe since the beginning of time and will ultimately determine its fate. As always, after his lecture, we'll have time for questions, so please wait for a microphone so everybody can hear your response and your question, and please join me in welcoming Michael.
Well, good afternoon. Thanks for coming. I'm going to tell you about an experiment that's occurring at the Large Hadron Collider, which is in Geneva, Switzerland. And these experiments and the collider itself are located 100 meters underground. And it's 17 miles or so around the ring here. And so it's at a lab that's called CERN in Geneva. And what happens here is that protons go around in these two different directions and then collide inside of the experiments. And this will all begin approximately a year from now. So if you zoomed in on that picture to here, you would see the Atlas experiment, which is this thing here. And it tells me that I'm supposed to show you the first animation, which I'm doing all these separately. So the first one is this one. So that you begin by accelerating protons around here and then into a bigger ring, and then the second proton comes in. And in a moment, after they've gone around, they will head into the Large Hadron Collider ring and start accelerating close to the speed of light. And when they get fast enough, they head into a collision point inside of Atlas, where we rotate here to see what happens, and we see a collision event that looks something like that. So back to the talk. So I wanted to impress you with a few numbers and start out with the Large Hadron Collider itself. And so it is the fastest racetrack on the planet in the sense that we're accelerating all these protons through the 17-mile ring up to very close to the speed of light. And this is 7 times the energy of any previous accelerator. And it's also, in some sense, the emptiest space in the solar system. You need to have the protons inside of a vacuum, and so there's actually 10 times more atmosphere on the moon than there's going to be inside the accelerator ring. Where the collisions occur will also be the hottest spot in our galaxy. The protons generate temperatures 100,000 times hotter than the sun, and it's equivalent to the temperatures a billionth of a second after the Big Bang. And in fact, that emphasis on the Big Bang is what occurred when the London Science Museum decided to put up an exhibit about the LHC. Their theme was Big Bang. So to do all this, even though these things are really monstrously large detectors, you have to build the most sophisticated detectors you could imagine, and they're having phenomenal precision to measure the tracks of particles that are going through there. So it's a mixture of huge size and tremendous measurement precision. We're also going to have a lot of data, as I'll show you momentarily, but to do this, we have to have really a large computer system with tens of thousands of computers connected over what's called the grid, which is sort of the next generation internet. So now turning to Atlas itself, the weight of Atlas is about the weight of 100 747 airplanes. But then I wrote empty because most of the weight in a 747 is you and your luggage and the gas. But so the size of it is about half the size of the Notre Dame Cathedral. There's a lot of wire in this thing. The superconducting wire, which is in the magnets, is about 76 miles long, but then you have all kinds of other wire, which is almost 2,000 miles more. So there's a lot of wire in here. And then there's all this data that we're recording, 3,000 terabytes, but since I didn't figure many people knew what a terabyte was, if you recorded all this onto CDs, which is not what we're doing, and stacked them on top of each other, they'd be up 4 miles high, kind of unstable. And then there's an awful lot of electronic channels, too. So this is obviously a complex operation, and so the question is clearly who's going to do this work, who builds and operates Atlas? And there are almost 2,000 scientists. This is just Atlas, by the way, not the other experiments and not the Large Hadron Collider. 2,000 scientists from 35 countries and a large number of universities and labs. And I thought it would be nice to show you some faces of actual people who were in here. So these are faces of some of the scientists in Atlas, just to give you a feeling of that these are real live people who have to do this. And where do they come from? Well, this is the sort of our map, world map, showing you the countries where they come from, covering obviously a fairly substantial part of the world. And even locally here, we have a lot of people. And I have some pictures of them. We built the very inner parts of the detector, which are referred to as the pixel part, and also another part called semiconductor tracker. And it's interesting to notice this group of people here from our lab. This is our fraction of those 2,000 people, but I wanted to emphasize that the young people are almost half the total of who actually does the work. So here's a cutaway view of it. And just so you wouldn't miss it, I wanted to emphasize that that's the people there. And here's a picture of it under construction a couple of months ago. And again, I wanted to remind you that there are people in this picture. The detector is now quite far along, and so different types of particles get detected by different parts of the detector. And so this thing here is a detector kind of particle called muons. This whole thing here was pulled out from inside and is part of a type of detector called a calorimeter. And then these are toroid magnets, which I'm going to tell you more about later near the end. Actually, I got an animation. So this is sort of what it looks like. And earlier on, before we filled it up with all the detector elements, it looked more like this, where you could see more clearly these magnets, which are used to bend the particle tracks. And wanted to emphasize, so you're looking here right along the beam line. So one beam is coming right out at you, watch out, and the other one is heading straight in. And again, there's a person here. So what happens when these two particles collide inside the detector? Well, this is what we'll see. I've zoomed in a bit, but we'll see tracks coming out from the center, and an event might look something like that. So all this is very impressive, but you might ask, though, but why are you doing all of this? And so I'm going to show you what the Discovery Channel did a news story on this recently, and I want to run their story. Now, hopefully the sound's going to work. I haven't actually tested it today. It's
called the biggest science experiment in the world ever. Its aim, to find out why we exist. So why is it buried so deep underground? Stay tuned. This next story takes place under the earth as well. In fact, it takes place 100 meters below the French-Swiss border. But it's not a volcano, it's not a lahar. It's very impressive because down there there's a machine called the LHC, designed by CERN, the European Organization for Nuclear Research. That machine is being engineered to answer some of the deepest questions we can ask. Buried close to 100 meters below the ground of France and Switzerland lies the biggest science experiment in the world. The LHC, the Large Hadron Collider, is a tunnel at CERN spanning a whopping 27 kilometers. To give you an idea of how big it is, just one of these 4 detectors along the tunnel is as tall as the Parliament buildings in Ottawa and as wide as 1.5 blue whales. Scientists have been waiting for 15 years for the final pieces of this to come together.
Longer piece, and we've cut out
It may
part
help
of
them uncover the biggest question of the ages. Why do we exist?
Well, I mean, it's a fundamental question, the basic question that mankind has been asking since the beginning. We're here 80 meters underground at the Atlas experiment.
If they see particles leak out of the accelerator, they believe it could be proof of other dimensions far beyond our meager universe. That's right, universe.
Gravity is weaker than the other forces. It's actually much weaker. Of course, we don't see that because the Earth is extremely big and it all adds up. But gravity is much weaker. And one idea is that it's weaker because it actually leaks out into extra dimensions.
Which leads to another obstacle. To prove this notion, they need to accumulate plenty of data. But how exactly does one store information for 40 million collisions per second?
Over several years, you'll be able to fill up enough CDs that'll reach the top of the CN Tower.
There are 3 levels of systems to record the information. The smallest amount will be recorded on something called the grid, part of which is being built right now. Forget textbooks. This could be the existential relief we've all craved through the ages. We may finally have an idea of where we come from and why we exist.
All right, so it's a little exaggerated, and so I'm going to tell you something a little bit more modest. Let's get back to the show. So, well, before I get there, I'm going to tell you what the New York Times did. The New York Times recently did a 3-page, full-page spread on the Large Hadron Collider. And among the things they said was, whatever forms of matter and whatever laws and forces held sway back then, meaning right after the Big Bang, relics not seen in this part of space since the universe cooled 14 billion years ago, will spring fleetingly to life over and over again in all possible variations, as if the universe were enacting its own version of Groundhog Day. And another part, it said it says that it describes discoveries such as a mysterious particle called the Higgs that is thought to endow other particles with mass, new forms of matter that explain the mysterious dark matter swaddling the cosmos, and even new dimensions of space. So here's some of the things which Dan actually said in the introduction, and I'm not going to read these to you. Instead, I'm just going to go on. But as I turn to the physics part of the talk, I wanted to emphasize what this cartoon says, which is that, here's me sitting over here trying to explain to you the detector and the physics, and here's you out here dreaming of something else. And, so the hard part is this person in the middle here, I guess, who has to try to somehow figure out where the middle ground is. So I'm going to start out, though, telling you about the Higgs Boson, which is one of the things that we hope to find there. And what it's about is trying to understand the origin of mass. Now, if you think about a composite particle, such as atoms, there's often the masses that give things their constituents. So if you looked over here, this is an atom, but the atom is actually made up of other things, such as the nucleus and electrons, and the nucleus is made up of other things, and the protons are made up of quarks and electrons, and those, as far as we know, are fundamental particles. And so the question is, where do they get their masses from? And why is it that the masses of different things are different? This mass and that mass can be extraordinarily different by factors of like 1,000. So what happened many years ago now is that the physicist Peter Higgs, and actually some other people too, proposed that all of space is permeated by a field, which we call the Higgs field after him. And quantum theory says that all fields have particles associated with them, so in this case we have a particle which we call the Higgs boson. So to understand how this might work, we have this cartoon, which I didn't invent, which says that if you want to understand the Higgs mechanism, imagine that a room full of physicists chattering quietly is like space filled with the Higgs field. A well-known scientist walks in, creating a disturbance as he moves across the room and attracting a cluster of admirers with each step. And this increases his resistance to movement as he gets this crowd of admirers around him, which in effect, he acquires a mass just like a particle moving through the Higgs field. And this explanation of the Higgs, which is, of course, grossly oversimplified, is due to a British physicist named David Miller, but is commonly quoted. In fact, it was in yesterday's New York Times mentioned. So what is it that we're actually looking for when we say we're looking for a Higgs boson or many other things? And this is just an example of what you might find. So in this particular case here, we see a jet of particles going this way, and then opposite was going a Higgs boson. But the Higgs boson decays almost simultaneously to being produced. It just happens very quickly. And then what in this case we assumed was that the Higgs decayed into two Z bosons, which are a couple of other fairly heavy particles, and that one of those two decayed into an electron and an anti-electron, and the other one decayed into a muon and an anti-muon, which are detected in different ways in our detector. And so what you see then is these two electrons that came from here and the two muons are coming out. They actually make it all the way through the detector, but we do track them and we know they're there. And then there's usually a bunch of other particles which may not be especially of interest to us. There are other things that are happening. So I'm going to change directions now, and although I'm not a string theorist and I don't want to tell you very much about string theory, I just wanted to emphasize that string theory has a couple of interesting predictions, although they're not unique to string theory. There are a number of theoretical problems. We have what we call the standard model that answers a lot of the questions of what we understand, but it leaves many things still unresolved. And theorists always like simplifications and deeper understandings, and we would really like to incorporate quantum mechanics, gravity, and relativity into a single theory. And so some of these theorists have proposed something called string theory. And for my purposes, what I want to emphasize is that among its predictions are that there could be extra dimensions of space and a new symmetry, which is called supersymmetry. So, and again, I can't tell you everything about supersymmetry, but I want to emphasize that it has one really fundamental prediction that is definitely testable. And that is that every matter particle, such as quarks, things made out of quarks, should be associated with a massive shadow force carrier particle. For those of you who know what fermions and bosons are, I've written that, but you can ignore that if you don't know what they are. So every matter particle should be associated with a massive shadow particle. Massive means something that's much heavier, has more mass. And every force carrier particle, as just the opposite, it should be associated with some massive shadow matter particle. And so what this drawing shows is particles here, the ones that we know of in our everyday life, but there could be this whole other set of particles which we haven't found simply because our accelerators didn't have enough power, enough energy to go find them. So that's what we want to do with the Large Hadron Collider. Now this, though, turns out has implications for dark matter, which I'll tell you about. So do you know what dark matter is? That's dark matter. And that's not dark matter. Well, actually, it is dark matter. Also, galaxies are, we think, filled with dark matter, as I'm going to tell you momentarily. So actually, we have a lot of evidence looking into galaxies and clusters of galaxies that there's something out there beyond what we can see, and that what we cannot see is what we refer to as the dark matter. So we have put together an animation to try to show you why we think this, which is go button. So we're looking out in space and focusing in on a spiral galaxy here in a moment. And the thing that's actually true about spiral galaxies is they're rotating, and they're rotating so fast for the mass that's there that we don't actually think that they should be stable. And given, if things are rotating around, it's just going to fly apart, which is what it shows here in a second. So it actually should just fly apart, and there should be nothing there to hold it together. But of course, we do see it there together, so I'm going to put it back together for you. So we believe that there's much more mass in there than the mass that we can see, and it's this combination of the ordinary mass and the dark matter that hold it all together while it's spinning around. So let's go now focus in on one of the stars inside of that galaxy, which turns out to be our sun. And then we zoom past a couple of planets on our way to a planet that you know. This is something, by the way, that was finished about 2 a.m. last night. So Earth isn't spinning here, but it's going to start spinning in a second. And then we zoom back down to Switzerland again, as you saw in the Discovery Channel movie. There's the Large Hadron Collider. There's CERN, the lab there. On the other side of the street over there is where Atlas is actually located. And if you were to sneak underground, there you would find the Atlas detector. And protons will come flying in, collide in there, and out of that we hope to see events in which we can see evidence for the particle that we think makes up the dark matter, and that's something that we're yet to see, but all right, let's see, how do we get out of there? So, given what we've learned already from looking at galaxies and clusters of galaxies, it looks to us that the part that you're made out of, you guys out there are just this little yellow wedge of ordinary matter, and there's a lot more dark matter out there, which is actually much more of the universe than this part is. And then, of course, there's dark energy, which other people can tell you about, but I don't have time to talk about dark energy, and it's actually not something we'll be able to look for at the LHC. So, what is dark matter? Well, actually, we don't know for sure. But being theorists, we have ideas. And one of these might be that they are, in fact, one of the supersymmetric particles, which is sometimes referred to as a neutralino. And you see strange events which seem to violate conservation of energy momentum, and particularly momentum, in that you see tracks going this way, and nothing going this way. And we believe that one of these other particles, the dark matter particles, which we can't actually detect, goes off. And so we see this imbalance. And by seeing these and similar events, we could do an analysis which would tell us whether or not we've actually found such particles. So now let's go back to extra dimensions of space, which somebody a number of years ago drew this way. So see this shepherd over here looking out into these other dimensions. So actually, extra dimensions have been discussed for a long time, and in fact, even famous artists have done it. This is Salvador Dali telling us about and he actually labeled his picture as being searching for the fourth dimension. It's actually, unfortunately, a bad reproduction here. And Picasso had this large series of paintings, or Dora Maar, in which he tried to think about looking at things through other dimensions also. So it's in art. It's in literature, it's in Star Trek, of course, it's in various other places. And the real question is it in science? And in particular, is it in more than just string theory? And so I come to a question, which is, which of these two forces do you think is weaker, gravity or electromagnetism? Or what did you think before you came in and heard what the guy on the Discovery Channel said? So how many of you think electromagnetism is weaker? You're all too chicken to say, huh? All right, so most of us, think at least of gravity and electromagnetism as being comparable. And what I have here is an ordinary magnet. And actually, the photographer is going to complain that I'm not in the picture, I guess. But anyhow, I have to do the experiment over here. Sorry. So I want to do a little contest between this little magnet and that huge object underneath, the Earth. It's a rather large gravitational object. And now, which of these two things is going to win? This dinky little magnet or all of Earth? And of course, the magnet wins. So, in fact, gravity is phenomenally weaker than electromagnetism, and physicists don't like mysteries of things that are different by many, many orders of magnitude. So the question is, why is gravity so weak? And now I'm going to, talking about extra dimensions is hard because you don't easily visualize a fourth dimension. And so what physicists sometimes do to visualize it is to say, all right, let's think of our existing world as a two-dimensional world. And then to think of an extra dimension, we'll go to the third dimension. So let's imagine that this is what electromagnetism is like. This is the world we live in, two-dimensional world here. And electromagnetism, if you have two charges, sends out field lines, and how close they are or how far apart they are tells you how strong it is. So this is a fairly strong field. So what happens if we go to look at another dimension? Let's say it was a fourth dimension, but we'll show it as a third dimension. Well, gravity is closely associated with space. And so gravity, if there are other dimensions, it will spill out into these other dimensions. Electromagnetism doesn't have to do that, and you and I don't have to. But gravity is, by general relativity, closely associated with space. And so if there's another dimension, the field lines are going to spread out into those other dimensions. And so what you notice, if you go back and forth here, is the field lines here are close together, and here they're much further apart. And if you start adding even more extra dimensions, of course, these field lines get further and further apart. And so what you're seeing is that this is an argument for why gravity might be so weak. So this is one of the reasons that theorists began to talk about why it is that we might have extra dimensions of space. So again, I'll just show you this. Close together, far apart when they're allowed to stretch another dimension. This is only one extra dimension. Imagine how far apart they could if we added 2, 3, 4, 10 extra dimensions in. All right, so how can there be extra dimensions, though? Well, one of the analogies we've made is think about an acrobat and a flea on a tightrope down here. The acrobat can move forward and backward along the rope. I'm going to imagine that this is a good acrobat. There's that other dimension. We're not going to talk about that one. But the flea can also move sideways around the rope. That's what's shown here. So the flea can do this, but obviously the acrobat can't. So it can move sideways around the rope. So if the flea keeps walking side to side, it goes around the rope, but it winds up where it started. Back to there. So the acrobat has one dimension, back and forth along the rope, and the flea has two dimensions. But one of those dimensions is a small closed loop. So the acrobat can see only the one dimension of the rope, just as we can only see our world in 3 dimensions, but that doesn't tell us there aren't other dimensions that we just can't see. And in fact, the reason you have troubles visualizing an extra dimension is because you can only see 3 dimensions. So, actually moving along faster than I thought. So what about mini black holes? Well, one of the things that happens if you have extra dimensions is that there's a possibility that gravity becomes very strong when you get into short distances. And what we do when we collide 2 protons together is we get particles closer and closer together, and then you have the possibility that you might produce a tiny black hole. And so these could be produced in the collisions at LHC, and the only reason they haven't been produced in other accelerators is they didn't have the energy to get the particles so close together that this might happen. But what happens is that they would very quickly decay and be detected by the experiments. And in fact, that the smaller the black hole, the faster it evaporates. So this all happens inside of our detector and looks like some of the other events that I've shown you. So then you might ask, and this, if you read the blogs, you'll see this on the blogs a lot, are mini black holes dangerous? Is the universe going to be eaten up and disappear as soon as we turn on the LHC? And there's a very simple answer to this, which is that cosmic rays are constantly bombarding Earth's atmosphere with far more energy than protons will have at the LHC, many, many orders of magnitude. So cosmic rays can produce anything that the LHC can produce. And they've been doing so for 4.5 billion years now. And yet, we're still here. At least I think we are. So the LHC just lets you see these processes in the lab. When they're happening in the top of our atmosphere, it's a little hard for us to tell what's happening there. And of course, we're at a much lower energy than some of the cosmic rays, but we can see it. This image was taken from the Pierre Auger Observatory, which is actually studying cosmic rays. And they, in fact, brag about the fact that they're studying the universe's highest energy particles. So this, in fact, is what an event in our detector, without showing you the detector, might look like. The white is this there to enhance it, so there's no white there. It's just that those are the tracks that we would see, and this is what an event to us in the detector might actually look like. So what's the schedule? Well, they start circulating protons in the ring next May, and they try to understand how it works, and they'll start out at low energies, and then they'll move on to try to collide protons, starting out first at a low energy, and then fairly quickly moving up to the high energy, and then start trying to accumulate actual results so that we can do physics. And conceivably, if there's something interesting and exciting and easy to do, we may find it even by the end of 2008, but the real excitement probably will stretch on to who knows when. So it'll go on a longer time. So I'm going to finish with 3 video clips just to show you what's going on. So as I think I mentioned earlier, one of the things that we produced here in Berkeley for Atlas was the pixel detector, which goes into the center and actually sees the tracks in the closest to the beam line where the collision occurs and follows them out. So this was one of our big contributions. And this is needless to say, a little speeded up, because it went on for many hours. But it's a long, big object, and they did it's a lot of work. They had to constantly check. Things were rubbing. You know, they had to make sure it wasn't going to break anything. No wires were cut in the process. And so this went on for many hours, but you're getting it in 30 seconds. Right near the end there, you'll see them all pose for a picture, if I can find this thing out of the way here. Yep, it went by you fast. So, and moving back to the talk. The next thing we did was, remember early on I showed you these giant toroids. Actually, let me go back to that and show you that and come back to this. Where was that? There. These are the toroid detectors. I took a picture once of one of these before they brought it down into the cavern, and it had 8 cars parked in front of it. So these are definitely large. And so what we did was, before they got to this stage, when they were lowering one of these down, there's a huge shaft that these things come down into the cavern, and remember, this is 100 meters underground. So we mounted a camera, actually somewhere in the center of it here, and so we could watch it, so you could come riding down with it. So where are we? Way down here somewhere. So I won't bother bringing it up, but anyhow, that's the. So you're gonna see the ride down now. Again, of course, tremendously speeded up. again, was probably several hours condensed into about a minute. So what we actually didn't show you here was what happened a little bit later. After this settled down, a couple of the French workers climbed on top to start setting things in place and noticed the camera was there, which they weren't aware of. And they looked into the camera, straight into it, and c'est fini, trying to get the camera to be turned off, and it wasn't turned off. And so then another guy climbs on, and they talk about this problem for a while because they don't like to have their work area filmed. So they then went down to, one of the guys disappeared and comes back with a big pair of clippers. And he looks in the camera and he walks behind and goes blank. So outreach has its consequences. All right, so you may remember, actually, let me go back again, that where was that? Down here somewhere there. And I showed you a couple of pictures. This one with it empty, but remember it got filled, so it looked more like this. And in fact, this detector ends up being, just practically dense with detectors and things of various sorts. So it's very hard to get around, but you're still going to have to work on it at times. Sometimes you can pull certain parts out, but the outer part cannot be pulled out, and so it's so the next video clip is what I call the Atlas crawl, and so but people are going to actually have to do this, and so I'm going to show you what it's going to be like to work in there, or what it actually is already like to work in there. Mind you, this is 7 stories tall, so if you start from the bottom, it's a long ways up. all in a day's work. So what we've done, because we have some really great clips, although that one I don't think's up yet, because we just finished sort of pasting it together yesterday, I think. We've been putting a lot of these pieces onto YouTube, and you can go to YouTube, The Atlas Experiment, and watch some of our clips. Some of them are ranked very highly, that you don't see it on this page, but on the second page that you get to by clicking here, you get to something which shows you what the rankings are and the viewings are. This was showing you what happened only a week after we'd put it up, and some of these things had up to, even then, 500 viewings. So it's quite interesting to, you can go there and see, and we'll be putting more and more stuff on as time goes by. Although you can also, I recommend you go to our web pages, those are our public web pages, which are shown up here, and that's the end.
We've got plenty of time for questions, so there's a question in the back here.
How long is the instrument scheduled to run for?
It will probably run for at least 15 years, maybe upgraded to have a higher rate of collisions by a factor of 10. They would much rather actually raise the energy, but that's phenomenally expensive. So basic answer is that most of the excitement should happen within 15 years, but a lot of stuff will be happening all along. But at some point you begin to, the statistics don't add up fast enough, and you really get more interested in trying to do something different.
Okay, so do you play hide and seek in that detector?
I can't hear.
I was asking whether you play hide and seek in the detector, but
You could.
That's a serious question. However, I know that one of the other experiments at the LHC, the CMS, has a fairly similar physics program. So could you briefly go over similarities and differences between ATLAS and CMS?
Okay. So this is actually something we've done historically. You find that you can't be sure that one experiment ever does something right, and there are a lot of wrong results that experiments have come out with over the years. And so having a second experiment or more is certainly really valuable as a check. And so in fact, usually when somebody makes a discovery, and there's currently at Fermilab, for example, there's 2 experiments, CDF and D0, and as soon as one of them thinks they found something, as soon as they make sure they get the credit first, they then go off and talk to the other guys, make sure that they see the same thing, because otherwise you can't really be sure that they didn't make some sort of mistake. One of the interesting differences, well, 2 of the interesting differences, CMS actually stands for compact something. It doesn't matter because it doesn't describe the detector, but the first word does, and it's compact. And it's actually half the size of ATLAS, but it weighs more than ATLAS, and they compensate by having stronger magnets to do things that we do by spreading out. They have a smaller cavern. Overall, almost anything that one of those experiments can do, the other can do. There's not really a tremendous difference. In fact, they were designed to be able to do everything, all the different types of physics that we're interested in. And so one of the types of physics, as I mentioned earlier, was we want to see if there's an imbalance of momentum on one side of the detector. And so that means you really need to have detector elements everywhere around it. And that's why these things tend to be built like a barrel, and then they have what we call end caps on the end to where you can't, because the barrel obviously can't go on forever. And both of those detectors are built that way, and but they use different types of technologies in different parts of the detector. So the detector has essentially, in ATLAS, 6 different types of technologies there, which are intended to solve different problems and look for different types of particles. But CMS is similar. There are 2 other experiments at CERN. They have different purposes, and their detectors are not the same type of detectors at all. One of them is called ALICE, or ALICE, and its purpose is to look for, we will not only collide protons, but they also collide heavy ions. And that's something that's currently being done, for example, at Brookhaven, and will be done at the Large Hadron Collider about 10% of the time, and during that time, this experiment will be the focus of attention. And then there's another experiment that looks at what are called B mesons, with trying to understand antimatter better. Okay.
You keep hearing that these experiments will recreate conditions of the Big Bang, and I suppose since you have higher energy, you can look a little bit further back in time than previous high-energy physics experiments. I was wondering if you could comment a little bit on what exactly that means, like how much earlier are you talking about, and does this bear any weight on inflationary theories, things like that?
Interesting question. We talk about going back to very close to the Big Bang, but Fermilab, for example, also does that. And you look at people do cosmic ray experiments, and they're, as I said, at higher energy. So there's not a tremendous difference. The difference between a billionth of a second after, or 10 billionth of a second after, isn't much difference as far as the physics we're going to see in that sense. It's more a way of saying just how energetic and what high temperatures these are comparable to. But it is true is that we see the processes that occurred at that time. And we see them with more and more energy, which means we can try to unravel. Understanding the Higgs boson will help us understand something about inflation, understanding any of these things. It's hard to say before we know what it is we're going to find. And surely if there are extra dimensions, that changes the whole scenario of what happened in the early universe. And many different things could have happened. And so we learn a lot about the early universe this way, but it's part of talking about it being a billionth of a second is just to emphasize the energies and the fact that we're looking at processes that normally wouldn't occur in the universe. Hi. You have to wait for a microphone, though.
Is it correct to compare the energy of mini black hole with the energy of cosmic rays? Because energy of black hole is very focused, and energy of cosmic rays is very diffuse.
What I was discussing was the fact that the energy in the collision of cosmic rays in our atmosphere can produce a mini black hole. I mean, again, a lot of these processes we talk about, not only for this, but for many other things, we're making use of E equals mc squared, that there is a relationship between energy and mass, and it produces massive objects. And these mini black holes might be very, very massive. In our units, something like, say, 5 TeV, which is a third of the energy that we put in. So all this energy of the collision of the LHC would go to produce the mass of the black hole. The black hole, like anything else we produce, is more or less at rest. But we're producing something, we've converted the energy into mass. And the cosmic rays can do the same thing in the atmosphere.
What does the name ATLAS stand for? Is it an acronym?
We no longer are willing to admit what it stands for. It was something silly. And it wasn't even the beginning of words. It was sometimes the ending of words. And it wasn't a description of the detector. So if you look at our website, for example, you won't find out what it stands for. It's power, whatever.
Okay, so I was wondering about the power requirements of LHC. For example, I know with high power laser experiments, a lot of times what they do is they pulse them and they have large capacitor banks that just dump a lot of energy in a very short amount of time. Does LHC work similarly, or does it just run continuously? And so how is that power provided?
Okay, so the answer is going to surprise you because, first of all, LHC uses almost as much energy as the city of Geneva. But it already did running in its previous incarnation. It's just a little bit more than that. But the power and the energy don't go to where you think. The energy is all stored in the magnets. The running of the accelerator, the beam of the accelerator doesn't itself have a large amount of energy. Most of the energy is going to power magnets both in the LHC and in the experiments. Because the experiments, again, all these are superconducting magnets. They all have to be cooled to a few degrees Kelvin. And so that's actually where it is. So the energy usage is fairly smooth. There's no ripples in our usage of the energy.
I imagine it's fairly radioactive inside the detector once you start collisions. So if something breaks once you're colliding, how long do you have to wait before you can go in and fix it? Or do you have to wait?
And of course, it depends where something breaks. The parts that I showed you is fairly far outside. And in fact, that's the only part that you can actually crawl through is what's called the muon system. And the rest of the detector has to be pulled apart. And I don't actually know the exact answer, but the answer certainly isn't minutes. It's days or weeks sometimes. It depends. And some places are just really would take a long time. But yeah, the inner parts can get very radioactive and take a long time to cool off. Maybe, does anybody, you know the answer? But yeah, you're not going to want to get into very close to the center of the detector after it's been running. It'll certainly be very hot.
Are there any other, one more?
They're talking about the International Linear Collider as sort of the next step. Would there be much difference in a detector for an electron-positron kind of machine? Or
so one of the interesting things is the International Linear Collider, which is at this point a hypothetical project which doesn't even have a country home yet. It could be in various places that are being discussed, would collide electrons and not protons. Now, your first thought might surprise you is that the electrons will have lower energy than the protons at LHC. But you got to remember that protons are not fundamental particles. They're made out of quarks, and it's the quark collisions that count. And so by colliding electrons, even though the energy is lower than that of the protons, it's not even the protons that really do the colliding. And so the difference there is that we know exactly what's coming in. When you collide protons, because it's the quarks colliding, and the quarks within the proton can have effectively different energies, you don't know what actually started. Plus, the other quarks that were in the proton cause a big mess too, and they're part of, I told you, the other spray of stuff that we're not interested in. In fact, if you looked at this, we tend to focus on these very energetic particles, but there's lots of lower energy stuff in there, and that comes because of the collision. It's much simpler when you just have electrons, electron and anti-electron, which is called a positron. It's a much cleaner event, and you can tell exactly what's going on in ways that you can't. So certainly you can do things. Now, it's possible, though, that the energy won't be sufficient to produce what we produce at LHC, in which case ILC would have a problem, and then you'd have to produce a higher energy machine. But the general idea is that we expect to produce some things that are within the range of an ILC, and that it could study things in the kind of detail that the LHC won't succeed at.
Are there any other, one more question quickly? And then
the questioner is walking around.
He's walking around, right, exactly. And here he is.
Okay, so isn't the top physics planned for the LHC in your experiment?
The physics plan. Is that what you asked?
Isn't the top physics planned with your experiment?
Top physics. So he's referring to finding top quarks. And so the first thing we're going to do when we turn on is not look for new physics, but actually try to find the kind of physics we found already studying at Fermilab at the Hadron Collider, and try to understand things there. So these Z bosons that I mentioned very early on with the Higgs are things which can be found easily at Fermilab. And so we will try to find these particles and make sure we can measure and get the right masses and see the decays properly. And then another thing that you produce at Fermilab, which was discovered at Fermilab, is the top quark, which is a very heavy particle. And we will certainly study the top quark. We will very quickly produce far, far more top quarks than Fermilab has ever been able to produce. And so again, these things, there was an old saying from one of my professors when I was in graduate school that today's sensation is tomorrow's calibration. And that's what it is for us. And so I wanted to actually have an extra slide here since we're not yet at an hour, which shows you something about how a detector works. So this is sort of a slice of Atlas here. And so here's the beam. This white thing is the beam pipe, and so particles get produced there. And they go through first what's the pixel detector, which is what I showed you being inserted, and then the actually also has these silicon tracker, and then there's something called the radiation tracker. All these things track particles. Then they're followed by two types of calorimeters who really, in some sense, as the word calorimeter suggests, just measure the energy. They don't actually see tracks. And so this is for display. This shows you what happens, but it's not what we would see. We only can measure how much energy is deposited in different modules of the calorimeters. The first one is made a bit lighter and is supposed to detect electrons. So what you're seeing here are different particles. So this is an electron coming through. This is a photon, but the dashes mean that we don't see it track because it's a neutral particle. So neutral particles, all these dashed ones, go through unseen. And so it gets seen mostly in here. Particles such as protons, neutrons, and mesons are tracked, then come through here and shower. These are what we call showers, and deposit their energy up in this part. And there are neutrons. Is there a neutron in here somewhere? Not shown. Neutral hadron, which would not have a track and would do, but out here it does the same thing as a proton does. And then a muon leaves a track in this area, isn't seen in the calorimeters at all, and then goes through the outer parts of the detector, which is where I showed you those people crawling through. So this is how we know, because the particle reached here, we know it's a muon. Because it showered in here but left no track, we know it's a photon. Because it left a track and showered here, we know it's an electron. And so various particles in this way can be told apart from each other, and then we try to put all this together. So a little add-on since I had the time.
Any other questions? One more, and we probably should wrap up after this.
What's the strength of the magnetic field inside the detector?
It's, what is it, 6 Tesla? Ron, do you remember? 4 Tesla? Somewhere in that range. 4? 4, according to Sandra.
And if there's no more questions, thanks again to Michael for that really interesting lecture.